Hey everyone, thanks for coming. It looks like quite a busy room. So essentially today I'm going to be talking about ways in which you can build robust machine learning systems. So stuff that's running in production, making decisions, affecting customers. You could also title this talk basically all the burnt fingers and ways which your machine learning system will fail that I've unfortunately experienced. So what is Ravelin and who am I? So I'm a co-founder and machine learning engineer at Ravelin. Ravelin is a company that ingests data from customers and from clients to help them protect merchants against credit card fraud. So if you are an app or you're a business and you take credit card payments, an unfortunate reality of life is that there'll be some level of fraud associated with that from people stealing credit cards and using them to transact in your business. So we use machine learning to understand the behavior of these people and to block them from using your service, so you never have to pay the fees in the first place. So machine learning forms a core part of the product. It essentially is like the very thing that we are selling. And some of the clients that use us are Deliveroo, Easy Taxi, Halo, and a bunch more. So a little about the specific problem that I focus on for my day job. Credit card fraud is a really big deal, as I'm sure you know. I'm going to hazard a guess that almost everyone here has been a victim of credit card fraud at some point in their life. Basically, an adversary will steal your credit card details. This will be through things like data breaches. It'll be through insecure, you having browsed on insecure connections, attacks, etc. And then they'll make a purchase using that card. This is bad for you, but ultimately you get the money back. So it's kind of, it sucks. But eventually you'll get paid back. It's a lot worse for the merchant that you bought the goods from. So if you bought let's say you bought a TV from Dixon's, if the fraudster buys a TV from Dixon's, you notice that was a fraudulent purchase, you'll get your money back. Unfortunately, Dixon's is out a TV and the cost of the whole TV. So they have to cover the loss plus a £15 to £20 chargeback fee on top of that. Pardon? They may do, they might not. A lot of people don't. So it's not often clear who pays for that fraud. Like most people think the bank pays for it, most people think Visa or Amex pay for it, but most of the times it's the merchant that pays for it. So if you're a low margin business, say you make 5% or 2% off an order, if you make 2% off an order, one fraudulent order is basically worth 50 good orders to get back up to where you originally were. So you can completely wipe out your revenue in one of these situations. So it's adversarial, so fraudsters are constantly trying to figure out what your machine learning system is doing and try and get around it. So it's an interesting problem in that case. There's a very true precision recall trade-off here. So false negatives versus false positives is a really big deal. False positives are basically all of the fraud checks that you'll have probably experienced as a customer, like you flew to America, you used your card in America, the bank thinks you're a terrible fraudster. False negatives are where you don't spot the fraud that did happen. And there's a very kind of fine tension between this. You want to stop some level of fraud, but you don't want to stop good customers at the expense of stopping that fraud. And mistakes cost lots and lots of money. So I'm kind of here to talk about software engineering. I kind of describe myself as a software engineer that does machine learning as opposed to kind of a machine learning researcher. So if we think about software engineering, we kind of build functions with some level of determinism, and we kind of try and prove them correct through testing and through all of these various offline techniques. So if you imagine you're writing sort of a lexer or a parser, there's a very kind of small world in which you've constructed where there's valid input and there's invalid input, and you kind of get to decide the parameters of that world. And there's kind of a sort of inbuilt sense of guilt and worry if you don't test your code when it comes to just like building, traditional software. Machine learning is kind of a whole other ballgame, I think. We learn functions from snapshots, so just from data directly. Truth is usually fuzzy, and truth is always subject to kind of usually the past behavior of your system as well. So it's a lot harder, and I think the kind of test coverage and what's acceptable to ship is kind of usually a lot less robust. And machine learning systems are often treated as very much a special snowflake when it comes to shipping things. And I think most software engineers would probably be horrified at the current state of machine learning testing, tooling, deployment, development, etc. And the key point is we learn models, and models are just views of the world that we've snapshotted into data. They're not magic, they're not free of biases, and they definitely need to be introspected. So why is running these sorts of systems hard? I'd say there's really high base complexity in doing so. So these systems are very complex by design. The bugs that happen with them are usually silent and kind of silent performance degradation. So I kind of compare them to data corruption bugs on hard disks. Like, you won't know about the problem until it's too late. You also train your models as if they have no impact on the future, when the very point of the system that you're building is to have some impact on the future. So the current decisions you're making are going to impact the labels that you get in the future, and we also kind of sometimes ignore that. And the loss function that we train for doesn't really usually represent the true goal. So like, say we want to train for engagement or for user happiness, you can't really express that as a loss function. So we end up trying to train on log loss, or we train on a very carefully constructed loss function, and it's not often clear that that's actually what we wanted to achieve in the first place when we built this system. So how can we stop machine learning systems from being this kind of special snowflake status and more just like normal kind of boring software? Wouldn't it be great if we can take things from software engineering that allows us to speed up, refactor, and upgrade with ease and apply them to machine learning? So I think it's important to realize that for a lot of people, machine learning is just an implementation detail of the system that you're building. If you abstract away everything to do with machine learning, usually you're just providing some kind of score function, which is like, given some customer data, please tell me how likely they are to be a fraudster or how likely they are to click on this ad. It's not really obvious to your end users that you have to use machine learning to do any of that. So when machine learning fails, you don't have a valid excuse of some hugely technical reason around machine learning why it failed, because they ultimately don't care at the end of it. I would say that the advice that I'm giving in this talk is around kind of medium to highly complex machine learning systems. So if you're just, if you're building kind of these basic simple systems, then you can kind of disregard a lot of what I'm talking about. But I'm talking about kind of time-dependent, real-world interacting machine learning systems, and that's kind of where a lot of this advice comes from. So I want to talk about techniques that you can use when training your models to basically ensure that they are robust and they've learned the things that you want them to learn. I don't mean like how should you optimize hyperparameters or how many folds of cross-validation are needed. It's kind of a lot more simple than that. I want to talk about how do we make sure that the world that we present to the model is the actual view of the world that we want to learn. And this is like the fuzziest questions come out, and you kind of need good judgment, but you usually get good at this through kind of black magic and a lot of burnt fingers. So ultimately, in kind of classification problems, labels are the ultimate ground, sort of truth of what we're trying to learn. But truth is an approximate notion in machine learning systems. So if we think about feedback loops in machine learning systems, say you have a fraud prediction system like we do. One of the things that we do is to prevent transactions that we think are fraudulent, because obviously that's the whole point of Prevalent. But when you say someone is likely to be a fraudster, and block them from ever making a transaction, you then lose the possibility of getting that label back about whether they actually were a fraudster or not. So you have to remember that like the labels that you are getting in are a function of essentially a function of the entire system that you've built so far. And if you think about the fraud that's still coming in, is the hardest fraud to predict, because it's the fraud that you didn't catch with your system. So you very much have to like be aware of this all of the time. It's the same in ad tech. I've never worked in it, but the ads that you present to a user are, the probability of clicking on an ad is a function of how prominently that advertisement has been displayed to the user. And you have to be able to control for this using your training techniques. But I don't have much experience with advertising. One of the biggest pains of my day job is the fact that the labels that we get back from fraud are super, super delayed. So if I'm a fraudster and I commit fraud today, there's a kind of probability distribution over how many days it will take you to detect that fraud on your credit card statement. and then the days after that it will flow through the global financial system, and then days after that it will eventually get back to the PSP where the original payment came from. So like this can easily take up to 2-3 months for a label to reach Ravelin from when we've made a decision. So when you're thinking about training your models, if you train on data from the last month or two, you haven't received the labels for the last month or two, because some of those transactions that haven't appeared as fraudulent yet are fraudulent, but you haven't simply got the label for them. So you then have to kind of discard a certain amount of your training data to be able to deal with that. There's also the notion of kind of implicit versus explicit labels, like hints versus actual true ground truth. So I don't know if you've heard of a system called 3D Secure in the UK. It will be the system that you have been kind of subjected to. You have to remember kind of your mother, your grandmother's maiden name, and the eye color of your cat, and all of these various things. And people, and it sucks, but people go through that. And usually going through that is a decent kind of hint towards the fact that if you pass 3D Secure and Ravelin thought you were a fraudster, then maybe we should update our views to take account of that fact. And I'm sure that in recommendations and all of these other sorts of fields, you have like clicks, non-clicks, looking at viewed it but didn't click. All of these sorts of hints which you can use to construct labels, but are not true labels in the sense of the term. And you should never really underestimate the importance of good labels. Basically, every problem I've faced at Ravelin has been due to bad labeling or incomplete labeling. So you'll have certain subsections of your data that never got labeled due to something your system was doing that deprioritized them from like actually getting a true label. And you just always need to be keeping an eye on this. It's basically where everything goes wrong. So how do you, well, looking at your training data, you probably need some kind of time machine if you're doing time-dependent modeling. So if you think about time leakage, when we train for fraud, we have to only take what we knew at time X to make that prediction. We can't use information that we know now. Otherwise, all we'll do is train our machine learning model to wait up until a very long time period and then say, oh yeah, they're a fraudster because they did 3 fraudulent transactions. And that's definitely not what we want to do. As I said earlier, we have to filter out some of our training data. And this is, I would say this is a bad thing to do a lot of the time because you're just explicitly biasing the data that you train on. But we have to take out the last month or two because it contains bad labels. We also have to take out certain various other sorts of things where we think that they're the kind of label coverage is too bad, and we'd just rather not train on them at all because we have enough data to train models as it stands. We don't need to kind of contaminate our training set with them. And then sampling is sometimes computationally necessary. If the above is here be dragons, there's a few dragons in this one. It's not super bad, but it's sometimes painful because you have to figure out things that approximately represent what you're doing in live, but aren't, you don't want to bias your training set too much, effectively. So if you've kind of followed these techniques when dealing with your training data, I kind of want to talk about testing your end-to-end system. So not testing in terms of performance on test sets, but in terms of how does the system work end-to-end, like an integration test. So machine learning is kind of unique and, well, relatively unique in the fact that it's made up of code. So the code used to extract some features and the actual data used to extract those features. And in my experience, you should assume that kind of either are broken unless you actually test them. So you usually have some kind of invariant in your data, which is this must go up in time per customer, the average must be 1, all of these sorts of things. And they're usually hilariously wrong until you've actually gone in and had a look at them. So you should really be testing your data. So there's NGuard is a pandas library for testing invariants. Things must be within certain bounds, etc. We just wrote a simple one, which is kind of more tailored to what we do. But they're very simple because pandas has a very nice API for explaining all of this stuff. But it's kind of just the constant sense of paranoia, which I want to drill into people, is that given the complexity of these things, you should be assuming things are broken until you've kind of tested them to make sure that they're not otherwise. So testing models is an interesting problem because there's some randomness when it comes to doing this. It's also, models are a function of data, so how do you test data? Like, it's kind of a bit complicated at the start to figure out how you do that. One thing that we found really useful is to have these sort of assertion sets, or things that Ravelin would be extremely embarrassed to get wrong. And we pull these out during training time, and we say, okay, this is effectively a unit test, like an assert true sort of thing. If we are a fashion company, we're trying to spot blue dresses, and the bluest of blue dresses comes up as red, then it doesn't matter what our test set performance or any of these other metrics means. Something is really, really badly broken, and we can go back to the start and figure out why that is. So we found this super useful. We also recently started generating sort of synthetic data sets. So if you have more complex sort of non-linear models, you want to be able to figure out what your worst case scenario is. So if you think of fraud, if someone has added 300 credit cards to their account in 10 minutes and spent £100,000, it would be very bad if Ravelin did not spot that. And we don't really see these examples in our training set because, hopefully we're a bit better than that. But we can generate synthetic data to know what we would do if these sorts of very, very bad worst case scenarios were to happen. And I think it's very useful to do because then you can start building some level of confidence and assertions about real world things that you expect your model to do without having to kind of find them in your training set. And if you have a really, really complex system with loads and loads of features, then this might be harder to do. But I would recommend it if you can do it. And inspecting your most misclassified examples, this is like where your model is desperately trying to tell you, like, there is something wrong here. This person is mislabeled. There is basically, either your model is very, very bad or it's trying to tell you something. And this is where a lot of the bugs that I've seen have come out. It's just like pure mislabeling of examples. It's just very interesting. This is where like a lot of your bugs will kind of manifest themselves as your model sort of desperately trying to tell you that something's wrong. So how do you make sure when you deploy models that they're actually any good? Are they better than the previous models? It's quite hard to know, but you should probably have some good sense of it by this point. This point you're switching environments usually, so you're going from offline to online, and you're sometimes also switching data sources as well. So you should be kind of rightfully paranoid at this point. It's like, okay, do any of these four, this 2x2 matrix actually match up? Hopefully they all do, but if none of them do, then like you're kind of screwed. So one of the things that has been really useful before we even press deploy on a model is the idea of sort of model provenance. So given that we have this kind of bit of code that has been learned from data, we need to be able to trace that back and figure out, okay, given that it's a subset of all of these other things, like let's make it so we can actually go back in time and figure out what did it. So who trained the model? Who can we go and shout at if things go wrong? When was it trained and on what Git hash? So what were the parameters of the model that were being used at that time? Which raw data was used? Where can we find it? Can we reproduce the whole end-to-end system? Which features were used? Which hyperparameters? And kind of really importantly, what was like training test performance look like? What is the distribution of the scores look like? So if your distribution offline is super different to online, then something's up. And we just stick these in a Python dictionary and kind of ship them out. Because if you can access them programmatically, you can then start asking more interesting questions of your system. Being able to say, okay, what are all the models that are in production that have a deviation from the original distribution of more than X? This is kind of invaluable for you being able to figure out basically when things go wrong. So when you want to ship models, I would really, really encourage you to not say, please go and rebuild this, MATLAB or R model in Java and come back to me in 2 months and let me know how it went. I would really try and use the same language, the same frameworks, the same everything to go from offline research work to offline production to online sort of production. And you really want to decouple the data source that you have from the way that you compute features on that data. So what I mean by that is that the way we do it at Ravelin is we have sort of a Go online service that takes the interface is simply just give me all of the features about this customer, given these sorts of fields of data, so transactions and orders and cards. And then when we do that online, we go and get this stuff from a Postgres database and give it to that function, and back come the features. When we do it offline, we go and get the data from BigQuery because it's much bigger and we can parallelize it. But the code that computes the features doesn't know where the data is coming from. So it means that we've kind of eliminated at least one of the rows in that matrix of the way that we calculate features being any different, which has made stuff a lot more easy to debug because we basically just wiped away half of the problems that could happen at that point. So when you deploy it, releasing gradually is always a good idea. Just A/B testing, ramping up traffic, all of these sorts of techniques. Just don't go, okay, the new model is going out now, and then change everything, because it never usually goes well. So one technique we found really helpful, and it's just kind of blindingly obvious, is just score them both at the same time in live, and then just take the things that have the biggest differences. Like you'll find really, really sort of spurious correlations. If your model has learnt to exploit structure offline that is not there online, you'll start to see it at this time point. And basically, this is where you should kind of be most paranoid about stuff. So as like a more engineering approach, just if you're going to make some sort of prediction, be that a recommendation, be that a probability of fraud, just store all the raw features that you used and the score that you gave, because you can use these to kind of unpick what went wrong. You can also use them as a source of future training data for other systems without having to go back and kind of recompute everything. So alerting instrumentation, if you use something like Datadog or Nagios or any of these platforms, just pump information about the distributions of scores that you're giving back, because then you can start saying, okay, well if Ravelin says more than roughly 1 to 2% of things are fraud, then Ravelin is wrong probably, and not the outside world. So we can do alerts on that, and we can alert the right people. And most importantly, measure the actual kind of goal that you wanted to do in the first place. Don't just measure precision recall and all of the other associated metrics. So automation, this is kind of one of the last things I want to talk about, but it's one of the things that we've invested the most time into at Ravelin. So we're a team of about kind of 4 to 5 data scientists. There's a mixture of like engineering focus, more research focus, but investing a lot of time into automation has meant that we're able to basically get away from a lot of the menial sort of tasks, and also stop wasting time waiting for jobs to finish, and also eliminate lots and lots of sources of bugs that come from not having automated stuff. So I think everyone's probably been there at some point when they're training models. Is like you have some data set, and then it's like turns into data brackets 1, and then you're like, okay, right, this is going to be the one, and then you put final on the end of it, and then there's like another final, and basically you're always making iterative improvements to what you're doing, and that's totally fine. You should be applauded for doing so. But at the end of it, it makes replication impossible when you want to figure out what was this trained on and what were the functions that were applied to it. And if you automate things, I think it makes you distill what you care about into processes. So it actually kind of clarifies what are we actually trying to do here, and is there a way in which we can boil it down into a process? And by the fact that we don't have to sit there, during the working day waiting for long jobs to finish, we can just kick them off when we leave the office. The team is order of magnitudes more productive, simply by virtue of not having to wait for it, and also not having to figure out bugs that are caused by this sort of stuff. So I kind of talked quite abstractly about things, so I thought I would go into a bit of detail. So this is what we do to train a model. We get a bunch of data from BigQuery, we pull it down locally, we do feature extraction stuff, so we pull features down, we sample them, we filter them, etc. Do feature selection, hyperparameter automation, and then we actually train the model. And like, given that we've trained this model, there's now a lot of interesting things that you might want to do to figure out, should I deploy it? But a lot of those things are also easily automatable. You can just pull down the live model that you have, you can pull down the model that you just trained, and you can do a lot of the stuff that we figured out, that you would only figure out at deployment time just offline. So you can say, assuming that you have a good match between online and offline, you can then do all of this. So in the morning, we get this kind of cute Slack notification that says, okay, I finished training with a model. Here's a little HTML report for you to read. So we then just go through that. It's got all of the important features. It's got all of the score distributions, etc. And then we can figure out, okay, do we want to deploy this model or not? So it's very nice in that we don't have to be kind of clicking through manual things to get to do what we actually need to do. And then finally, we just save everything to S3 or to Google Cloud Storage, because then we can get back to this at any point in the future. So that was kind of a bit of a whirlwind tour through what I've been through at Ravelin, building this stuff. I'm very happy to answer questions afterwards. But to summarize, this is what I would do if I was to sort of do it all again. I would just test everything ruthlessly and start really, really simple. I'm kind of convinced at this point that unit tests are helpful for figuring out that your code is correct, but they're much more helpful for preventing regressions. So I wouldn't lean on them being like the source of, if your test pass, then the system is fine. That's definitely not true. But they certainly can't hurt. Paranoia. So models will cheat ruthlessly at whatever you give them. So there's some kind of hilariously awful stories about models cheating in the data that we've given them, and then if a certain value is above X and another value is below Y, then everyone is a fraudster, for example. Thankfully we catch these offline, but basically, yeah, you should constantly be looking out for this stuff. And then reproducibility and automation is kind of paramount when you want to build robust systems, because then you can go back and figure out what went wrong. And more importantly, how you can prevent that in the future. Maybe it was somewhat of a depressing talk, but you should try and have fun whilst you do it at the same time. But thank you very much. Happy to take questions. Go ahead.
What's a good way to find out if a model is a cheater? Is there some automation there as well?
So in that kind of particular, so the question was, what is a good way to figure out if a model is cheating or not? We like to think that we would have caught these in all of them ahead of time, and the truth is we have never managed to catch them ahead of time because they're always so different. I don't think you can do very much apart from kind of have your wits about you. If you start seeing strange things happening it's usually in production. Not when we are actually sending scores live, but just kind of when we're logging scores, we'll start seeing weird things like every new customer is nearly very, very likely to be a fraudster. And it's these sorts of things, you could say, oh, well, yeah, new customers, blah, blah, blah. In reality, you kind of just have to have that sort of sense about you, no, this is a point at which I should be very paranoid. And digging into the structure of these will kind of tell you about why it's done. So unfortunately, we've never managed to automate them, but they are, yeah, they're super painful, the worst part. Hey.
You haven't managed to automate much, or have you found any useful tools for automating the extraction of information around your model parameters or what data went into it, or is that fairly manual, someone signs off on it?
So yeah, so the question is, have we found any good useful tools and processes for automating and figuring out what went into models? So we use Luigi to do a lot of this orchestration. There's other things like Airflow. Basically just choose a task manager and stick with it. What we've ended up doing is we have this sort of audit record, which is that dict that I said about test performance other stuff like the data that went into it goes into there. Basically, all of the useful information about the extraction goes into this dictionary. So we can look at that in the HTML report, and then we can also look at that programmatically. We haven't found great tooling for actual model deployment and kind of serving and introspecting these sorts of things in live. So we've just had to expose them via APIs. But I hear people talk about kind of Science Ops, I think, is a sort of platform for deploying models. But we found tools, open source tools, kind of lacking in this area. But they're not too complex to build either. Let's go with you.
How do you version your data?
How do we version our data? So our data is pretty much immutable once we've done the extraction. So if we were going to go and do a manual thing to the data, which is I don't know, say everyone called Stephen is now a fraudster, we wouldn't go and touch that data. We would build a new version of the binary. So the version of the binaries that we use are also chucked into all of the extracted information, and then we would put that in in the model directly. But we don't really do anything around saying this is the version of the schema or whatever it was, because the model knows what features it wants. So as long as you don't take features out, then you don't really have those sorts of compatibility issues. But I don't know if I really answered your question.
I mean, you're saying that because you have one set, and because you know the data file in which the model is trained, therefore you get that
Mm-hmm.
your version of the model history.
Yeah, we try not to touch things and then not, touch data files and not tell anyone about it, because that always leads to bad things.
How do you link your provenance process to the kind of the sign-off, like a user sign-off? So once you kind of deploy a model, presumably your client will say, we are happy to run this in production. How do you kind of link that with your provenance?
So the way Ravelin works is that essentially we would not like you to know if we deployed a new model or not, apart from better fraud, lower chargeback rates and lower false positive rates. So we don't do so much around asking people, but we're definitely super paranoid and very much on offline testing before anything goes to production, essentially.
So your models are kind of common to all users? You don't have a merchant-specific models?
Some are and some aren't. It really depends on the use case.
I see. Right.
Sorry, I think you've been waiting.
Thank you for the talk. You
Thanks.
were talking about a lot of practices and methods and things like this which normally require getting the people in line and aligned to do this. So can you tell me if you have had difficulties doing this, or what kind of things have worked or haven't worked for you trying to align your team to apply these practices?
Yeah, that's a really good question. So the question was, have we had any difficulty in trying to introduce these practices, get people to use them, get teams sort of aligned around it? So I would say no, but a lot of these practices were not what we started with. They're sort of emergent behaviour of having our fingers burnt and then going, okay, that was a bad thing that we did, let's not do the bad thing anymore. And then this has kind of become, I guess we haven't had any problems introducing it because it's always been a reaction to a bad thing, and which is kind of nice because no one really needs convincing at that point. Sorry, go ahead. Yeah, you.
You seem to be working in a problem that is by definition hard to test. As you said, fraudulent behavior is evolving over time.
Mm-hmm.
So I'm wondering, is your strategy to always try to capture, assuming that that customers always change this behavior, is your strategy to try to capture the behavior that previously has already been shown to be fraudulent into tests? And is there any way to capture this? Is there any way to measure whether your algorithms capture this anomalous behavior, this new strategy that people are using to fraud the system, and test that? Is there any way to test the fact that these things that you don't yet know, essentially, because you're trying to do anomaly detection here?
Mm-hmm.
I'm wondering whether there is any way to test against that as well?
So I think the question was, fraud is constantly evolving, and what you stop now is not necessarily what you are going to stop in the future. Is there a way to test against that? I'm not really. We haven't kind of. We've obviously thought about it, but we haven't. You know, it's also a very hard question. Like, how can you test the behaviour of something against something you don't know? So we do a lot of. We have sort of infrastructure that will spot things that are different. So if you think about kind of very high cardinality variables like emails, email providers, all of these sorts of things, we have this sort of online learning infrastructure that given some labels that come in, we're able to quickly react and say, okay, this level of fraudulence has increased very highly to the point of which like this contributes a kind of significant amount to your score. But we don't, apart from like various anomaly detection techniques, we don't have anything, I can't think of anything specific to answer, I'm afraid. Sorry, go ahead.
Two questions. So, how often do you retrain your models, and how do you do it? Do you have like a moving window of some kind? And the second question is, where do you like store all this model metadata, like things like parameters?
Sure. So, first question is, how often do we retrain models? It really varies. So, like we usually go for anywhere between like 2 weeks and 2 months. It kind of depends on what we're doing at the time, because there's a huge lag from, like I said, from deploying a model to getting any feedback on whether that model is good. You can build models that predict, given the number of chargebacks that you've received so far, how good is this model? But you kind of want to wait a little bit of time to see it bed in before. So that's why we don't do like, completely like retraining every night and shipping. But we could, but it's not like a priority for us at the moment. And then for storing model metadata, we did the easiest thing at the time, which is just to pick all stuff out and to load it back in. We're now right in the midst of we're forking a version of scikit-learn, which is essentially going to deal with missing values a lot better. So there's a problem in decision trees, which is if this value is not present, what do I do? So you could build another variable that says, okay, it's not here, or you can impute this variable with a very large sort of negative number. What we've tried to do is we built a technique which will go down trees with the lowest sort of deviation from the current probability of fraud. So basically don't change your decision too much given that this variable isn't here. So we pickle everything into these models and we store everything as a dict, and then we can load it all back out afterwards and we save it all as HTML files. And I'm afraid that's the last question, but please come and grab me afterwards. And thanks for coming.